things that are changing, and we try to find them in real time. And
Oh,
those are
cool.
the things that we are really going after.
Okay, so you find something that's changing, then you would focus specifically on that. Do you have recent examples?
Right. So for instance, things that change in brightness suddenly can be supernovae, which are exploding stars.
Yeah.
Or for stars within our galaxy, there can be flaring stars. So just like the sun has solar flares and they send a lot of energy towards us, there are stars that can be flaring 1,000,000 times more than what the sun does. And so clearly, it's good that Earth is not around such a star, otherwise we would have been toast long, long back. But those things then change in brightness by several magnitudes. So some of them could, in principle, become visible with the naked eye for a short bit, and then they fade quickly. So the interest is that when they're at the top of their brightness, a different kind of physics can be seen. And so that is why we want to catch them in real time. And once we find them, try to use other telescopes to point to them, take their spectra, so that we can learn what elements are being found in there, what is the physics that's happening there at the time.
So how quickly does a solar flare fade from visible knowledge? Like if you caught it?
So solar flare is fairly rapid in general. It
Okay.
depends on the energy, of course. And so the corresponding stellar flares can be minutes to a few hours, perhaps, again, depending on the type that it is.
Okay, so how, this must be very recently that you've been able to even just catch a solar flare. How many,
So we ourselves don't catch solar flare. There is a separate set of
Okay.
astronomers who are solar astronomers, so
Yeah.
who keep on looking at the sun.
but your area of expertise is transient astronomy.
Right.
So want to go into depth on that a little bit?
So again, what we call as transients are these objects which change in brightness rapidly. And rapidly, the word rapidly can mean different things for different people. For some people, it is a matter of seconds. For some people, it's minutes. For some people, hours is also fine.
Yeah.
And my personal interest in this, especially in the last few years, has been trying to classify these objects as quickly as possible with as little data as possible. Because if you keep on taking observations again and again, then you're going to get a better handle on how the object is varying and be able to say that. But if you want to classify it quickly and do follow-up observations on that, then you want to be satisfied with only a few points and be able to classify. And the reason for that is that with recent surveys, you can find hundreds of thousands of such sources every night.
Yeah.
And so that is where the interesting part of classification comes in. So we'd like to use the computers to do the classification.
Okay. So how do you use the computers to narrow down what you're focusing in on?
Okay.
Yeah.
So what we largely use is machine learning.
Yeah.
So computers, machines, we try to teach the machines the kind of patterns that we expect. And if we are good at doing the training, if we have a good set of examples that we can teach the machine with, then the machine can potentially learn. And so training sample, getting a good training sample is of critical importance. And for that, of course, we have the experts. So astronomers, domain scientists look at a few objects, and then based on that, they can say, okay, this is a supernova, this is a blazar, this is a flaring dwarf star, and so on. Or this is a dud. This looks like an object, but really it is something bad happening in the camera, so it's an artifact. Or of course there are asteroids, because asteroids keep moving. So I'm looking at a part of the sky. There is nothing there right now, but 5 minutes later I take an image and there is something there. So one could think that there is something that was very faint there which we couldn't see before has suddenly become brighter. But the other possibility is that an asteroid had just moved into that spot. And that happens all the time because there are so many asteroids around, right? And so we have to be able to then separate those objects also. So we have a set of asteroids that we know about, so we compare against their motion. We have a set of known variable stars, we compare against that. We have a set of galaxies, because supernovae, when you look for them, they are in external galaxies, so you look for them. So those are also there. So you compare against this large number of lists, and when you compare against existing lists, then you can say, okay, these things that were not there before seem to be getting brighter. And then once you do that, then you can characterize them in terms of, did it change in 5 minutes? Did it change in 30 minutes? Did it change in 2 hours? Was it there last night? Was it there last week? Because you can look at all the archives too. And that is what gives us a handle. So we can come down from these 100,000 to perhaps the 100 most interesting objects But even 100 you cannot follow up spectroscopically, so we want to go down to even a smaller set of objects.
And spectroscopically, when you find the star that you're interested in, what is the next process then?
Okay, so there typically what astronomers do is that they have a network, so that the interesting thing that happens is that, consider we are doing the observations from Palomar Observatory. So it is 8 p.m. here. Now in Europe, they are 9 hours ahead of us. So it'll be a different time separated by that much amount. So it's already morning. But Hawaii is behind us. So if it is close to the morning and we find an object close to the morning, then we ourselves may not be able to follow it up because there is twilight now.
Yeah.
It's getting too bright. Europe cannot observe it. But we can send the coordinates to Hawaii and they can observe it. And then there can be another telescope on the other side and we can have a whole thing. So in fact, in Santa Barbara, there is this organization called LCOGT, the Las Cumbres Observatory. So their phrase, their not motto, but what they say is that the sun never rises on our empire, because they have telescopes all around the earth. So there's at least one telescope that they have always where there's night and they can do the observations. So these networks can help us classify, so we can shift it to different groups and do the observations.
So what would qualify something as so special that we would want to be observed around the night sky? What are we looking for there?
So we are looking for everything, because what we want to do is that understand the whole structure. So within our solar system, we have planets and asteroids, and then as we go outside, there are different kinds of stars. So the Hertzsprung-Russell diagram has all kinds of different stars. That is what we need to understand within our galaxy. But then when we go outside, there are even brighter sources like blazars, which are very large radio sources at the centers of galaxies, which are spilling out huge amounts of energy.
Yeah.
So we want to do a census of the entire universe in order to understand how these things got put together, what are the timelines over which these things are happening, and whether we can predict what can be happening over short terms or long terms.
Yeah, I'm very interested in the time scale of this to begin with. Like, has technology helped you to see much farther in the sky or deeper into the past? How do you put a time stamp on these stars, that kind of thing?
Right. So as we have been able to build larger and larger telescopes, like we have 10-meter size telescopes now.
Yeah.
So compare that to our eye, which is about 1 centimeter. So when you have a much larger telescope, you can gather that many photons. And as you gather that many photons, you can see fainter. And when you can see fainter, then you can see objects that are farther away. So that is how you can see deeper in the sky. And as far as time stamping it goes, that is where the spectra come into picture. So the universe, as we know, is expanding. What that means is that galaxies are all going away from each other.
Yeah.
And then, just like a train, when it is going away from us, because of Doppler shift, we hear a different frequency. Similarly, for these objects which are going away from us, the wavelength shift redward, and that is why it's called a red shift.
Yeah.
And so you see the standard lines shifted to the red, and by seeing how much they have shifted to the red, then you can make out how fast they are going, and that is the number that we use for the expanding.
How do you know that it's not just a redder star?
Right. So what happens is that there are multiple lines in a spectrum, and when you see a redshift of say 1.5, that means that that is the factor with which things have shifted, and then all the lines have shifted. And the main thing is that if you have a line at 3,000 and another at 4,000, it's the same factor. So the difference between them doesn't stay the same. It's the ratio between them that stays the same. So you can see the entire spectrum being stretched out.
Okay.
And that is what I can tell you.
Interesting.
And then experts can normally use only 2 or 3 lines to do that, but it's recommended that you fit a plethora of lines, take a dozen lines and then do that to be absolutely sure. And then there are of course cases where you can have multiple objects that are close to each other, or there can be absorbing elements between that object and you. So you can see 2 sets of lines. So you can get 2 different redshifts in the same object also.
Cool. So what are some of the oldest things we can see in the sky?
With the largest telescopes, these would be galaxies that are far away or some quasars that are far away. So quasars at redshift of 6, 7, something like that would be the farthest one. But normally those are also very rare, because given that they are really far away from us, what that also tells us is that they were also created fairly early on.
Right.
And we have to really look, and they're fainter typically.
Right.
So we have to really go through large sets of data to look for them, and that's non-trivial. So there are these big surveys that go and look for that, and those quasars then are very useful for cosmology, because then you can try to bring together this distance ladder, try to determine when the universe was formed, and try to get those numbers more precisely.
Yeah, so the older we can see, the closer we get to discovering how it all formed. Is that correct?
Yes.
Okay. And also, these very old, distant galaxies might not exist currently in our present. We're seeing the light.
Correct. Yeah.
Okay.
So time has passed. So consider a galaxy that is say 10 billion years old, and so we see it today as it was at that time. But in 10 billion years, all the stars would be gone, or they would have faded, and so on. So talking about light and distance, I remember an interesting story. So the Griffith Observatory was undergoing renovation for several years.
Yes.
And when they reopened, they set the telescope to point to a star that was about 76 light years away. And the reason was that when the Griffith Observatory opened the very first time, not at that time, that was the period that has elapsed. So they were looking at a star which had, the light had started at the time Griffith Observatory first started, and now we're seeing it when it was finished. So you can play tricks of that kind.
Yeah, it's wild how you can do that. Now, light is a constant, but there are things that can slow it down. Are there things in space that might prohibit its speed?
Well,
I know on Earth we can go through like an artificial force slowing down
right,
of
there are
light,
many things.
but-
That's not my area.
Okay.
And so I don't think I can go into too many details related to that. But yes, I can imagine as a science fiction person,
Yeah.
I can say that yes, definitely it would be of interest to find areas in the universe that will slow light down in that fashion, and be able to do that. In fact, that reminds me, I do have a story which involves mythology and astronomy, where what I did was that, so in Indian mythology there are all these gods, there is a hierarchy of gods, and when the lesser gods cannot handle a problem, they go to the highest god and say, oh, you are the only person, or you are not person, you are the only god who can save us from whatever is happening now.
Yeah.
So such a thing has happened, and then in parallel I give a physics explanation of whatever is happening, and in that case I have invented in fact a field that does something to the light. So in fact all the images have vanished in that story. So the mirrors are not showing you images, the optical telescopes are not receiving any photons, and that is because someone has been naughty or angry, and they have requested the highest god to remove all things that are equivalent to his name, which happens to be an image. And then so this interplay of
Oh, that's cool.
you can have force
so
fields that
taking,
do that.
taking away the light and,
Right,
and
yeah.
everything. A lot of what you're studying though is light. If you're looking for the varying degrees in the stars and light, but it doesn't. Do you just auto-calculate with the speed of light and assume that there is nothing slowing down that time?
Right, of course, yeah.
Yeah.
So all the stars in our galaxy, they are really very close to us compared to the large distances outside the galaxies. And in fact, if you look at the redshifts of the stars in our galaxy, you don't even notice a redshift in general. So there are other motions that are happening, because there can be binary stars that are going around each other. And when this star is approaching us compared to this star that's going away from us, so there is relative shift that you can see between them.
Yeah.
But the absolute shift is not too much, it's just equivalent to the distance, the rate speed at which it's approaching you locally. But those speeds are far, far less than what you see for entire galaxies going away. Because also the other thing that you should remember is that as the universe expands, it's not the galaxy that is also expanding.
Yeah.
But when you blow into a balloon, it is like things that are fixed size on the surface of the balloon that are going away from each other, rather than a circle that you have drawn on the balloon which can also expand. So that's not what's happening to the galaxies. So it's the fabric itself that is expanding.
Do you ever see any new galaxies forming?
Not in our lifetime, not individually, but
Yeah.
that is where statistics comes into the picture. So
Okay.
if you look at all galaxies, then based on the stars in them, you can see which are the more nascent galaxies, more the younger galaxies which may be having more star formation, or galaxies which are much older which have ceased star formation, and you see mostly old population stars there. So you can see these different things.
Are they in a specific like area in space, or the newer ones forming?
No, so that's a question of interest, because you asked earlier about the most distant galaxies, and by that reason they are very old. So whether we find young galaxies far away also. So we don't find too many young galaxies there, but there have been some surprises where some things have been noted off and on. So
yeah, that's so strange. Because you would think that a younger galaxy would be like closer together in the way that everything is moving apart. There's more matter to form new things here. There's less
there's
matter
a lot of
out the outer reaches, right?
No, so there's a lot of recycling that happens of matter, right?
Yeah.
So when stars die and they shed their matter out, that matter is what is going out, and that can lead to second generation stars.
Yeah.
Right. So for instance, all the gold that we see here, much of that would have formed in some supernova explosion or some gravitational wave events. In that.
Yeah.
So that is definitely a second order thing that we are seeing, because inside a normal star, a first star that has been formed only from hydrogen and helium, you can go typically only up to iron until the star explodes. Only then you get the higher elements.
Okay.
So that recycling is happening all the time.
Okay, cool. I was on a different track there a second, thinking about how these things form, but we'll get back to your areas of expertise. So what are we have bigger pictures of what these can solve, but you're looking for specific problems. What are the kind of smaller things that you're looking to solve here, especially with data research, data gathering?
So I officially belong to the Center for Data-Driven Discovery at Caltech, and so what we believe in is that if we have large enough data sets, you can look for interesting patterns in them and try to discover new things. Now, not all patterns, not all correlations mean causation, but that is where the domain expertise can come in, and you can find the patterns first and then ask yourself whether those patterns mean what they seem to be suggesting.
Yeah.
So what we are trying to do in these big data sets are trying to understand different signatures so that we can do these classifications. So the machine learning part that I mentioned earlier, we do it in two ways. So one is the domain experts telling us what specific objects are and using that as a training sample. But we also use public platforms, citizen science platforms, where we can make small tutorials for simpler things for people and then show them large number of different kinds of objects, and they can mark them for us. So that then forms a good training sample.
Yeah.
So earlier, again, what would happen is that if you're looking at hundreds of objects, an individual person or 2 or 3 people could look at those 100 or even 1,000 or even 10,000. But given that we find hundreds of thousands of such objects every night, then we cannot look at them, and that is where first we get a small set and then get these computers to do the classification. So I work in specifically this classification area right now. So one of the areas that I've been getting into is deep learning, where one builds very large such layers of objects, layers of networks, and then within those networks try to classify kinds of objects. So I think deep learning became fairly popular some time back because the game of Go, the expert was beaten by a system that learned from a deep learning network. And their older examples were given, older games were taught to that system to beat the best person who could, the Go player. But then there was a second system which taught itself from scratch and beat the first system 100-0.
Yeah.
So all these patterns that you can be developing in that. And so with our kind of thing, what we are looking for, if I observe a particular object, what we do is that we observe them again and again. So we get a time series. So we see how the brightness is varying, and that is what we want to use to say what it is. So suppose I have this time series which is very irregular. I can ask the following question. What is the mean value for it? What is the median value? What is the amplitude difference between the brightest and the faintest point? Or what is the skew? What is the kurtosis? So I can define, say, 50, 60 such statistical values. Then what happens is that each star for me becomes a set of 50 to 60 numbers.
Yeah.
Now, originally the time series may have had 10 points for a star, 100 for another, 200 for a third one. So that's very uneven. But I can convert these sets of different numbers into the same set of numbers now. So the 10 can become 50. That's not a good thing because you're trying to invent data from fewer data points. That's generally not good. But bringing 100 to 50, it's kosher, it's fine.
Yeah.
Or 200 to 50. But you bring all these time series to a 50 set of 50 numbers.
Yeah.
Now this in some sense is like a 50-dimensional space. So this is a 3-dimensional space in which we are.
Yeah.
But once we have a 50-dimensional space, then you are trying to bring these things apart in the 50-dimensional space. And then you form clusters in them. And then you can start saying, oh, this set of objects are on one side, so they should be all like each other. And if you know the classification of one or two of them, then you can say what the rest are. Similarly, you find a cluster somewhere else, a cluster somewhere else. So especially when you are looking at quasi-stellar objects, quasars, which are at the nuclei of large galaxies, they look like stars because they're so far away. So for all practical purposes to a telescope, it's a star. But when you look at them in two different filters, it's the color, the change in brightness between the two colors that tells them apart. So when we do this study and we do simple plots, all the stars will be along the locus, whereas these other objects will be scattered around it. So just by looking at that, then you can say, oh, these are the quasars that I was looking for. So you can do these, pulling them apart in a much higher dimensional space. Sorry for the long answer.
No, that's awesome. How quickly are the machines learning this, and how much more data are they able to process? So like in 5 years, are we going to have a map of our galaxy with everything defined? Like
Actually, 5 years is a good timeline for the specific wording that you use, map of galaxy.
Yeah.
Because just last week, the European Space Observatory, Gaia, they released their second data release. And that observatory has got exceptional astrometric accuracy, that is positional accuracy.
Yeah.
And one main aim that they have is making the map of our galaxy.
Oh,
so they
cool.
have, and it's a 5-year mission. And they are through 3 of their years. And what they have been doing then is that looking at detailed arms. So our galaxy has seen a very violent past as well. It has interacted with other galaxies, but we have not been able to see in great detail what these interactions have been. But now, if we see a specific kinds of stars have in a specific arm-like arc, then we know that that is an indication of a past interaction with another galaxy that may have just passed by us, pulled a swath of stars outside, which changed in some fashion, and we can still see them.
Oh, that's so cool. So, and they're definitely helped with the machine learning. This wouldn't really be possible to do without technology. Very cool. So dark matter, it's a, I know no one has figured out what it is.
Right.
Insight from you on this?
Again, I don't work directly in that area, and I don't have necessarily my favorite type of thing that will give rise to dark matter. But the current physics and current understanding that we have of the universe, that does suggest that dark matter should exist.
Oh,
And
okay. Well, it does, right? So it's good
as far
that
as
it
we know,
should,
the current
as
theories.
far as we guess. So how has all of this work played into your creative works? Because you've taken the leap and done, you've been published for scholarly journals, but also for creative nonfiction works. How does this kind of...
Right, so in terms of non-fiction works, besides the papers that I write from my usual astronomy thing and the data science thing, I also write some short articles trying to popularize astronomy, because many people are really interested in astronomy, but they normally stop at a level of observational things, so they don't understand the relationships between large things. And because of that, and because many of these things are very non-intuitive, they sometimes have misconceptions. And astrology is one area that I like to attack because of the astronomy part. So for instance, people think that planets affect you directly, but then if you show how there are these limited number of forces and only gravitational force really works at a large distance, and then if you compute the effect of gravitational effect of gravitational force on you, then how much it is compared to what the planets are going to have. So when a child is born, for instance, the doctor exerts more gravitational force on the child than, say, Jupiter does. And people don't understand that because they cannot do back of the envelope calculations, because gravitational force is directly proportional to the two masses and inversely proportional to the square of the distance between them. And Jupiter is so far, 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 far away, though it's the biggest planet. It has negligible force on us compared to the humans around us. So things like that.
Interesting. And you've incorporated that into your fiction works.
Yes, so I write fiction, short stories, science fiction in Marathi, my mother tongue.
Yeah.
And about 15 of those have been published in magazines in India. And I incorporate a lot of astronomy in them because I try to write hard science fiction. And then again, I also, though I'm an atheist, I also incorporate mythology because mythology is fun, how things evolve. So I try to connect the two together, and not in every story, but that's where I find quite fun connections, because there are many beliefs that people have which have come from some kind of theology, and people also try to connect the theologies to older science, claiming that, say, science may have existed at the time, a different set of concepts. So that's what I like to play around with.
Okay, so you incorporate mythology and the evolution of both the universe and the people.
And human evolution too, actually. Yeah.
Okay.
So DNA is one of my favorite topics.
Okay. What are some kind of discoveries you've made about people while searching through your creative works?
Discoveries about people?
Yeah.
You
know, it's another observation to
Yeah.
look at people. And
So
read
I can
them.
tell a little bit based on the feedback that I've received. So
Yeah.
my earlier stories used to be very dense, where I used to combine too many concepts into one story, and there used to be hardly any dialogues in them. And this would be a science narrative kind of thing, but with a fictional overtone. And people would say that it's nice, but I don't think I understood it. So that's where I started going into dialogues, and then I wrote a few stories that were dialogues only, so it was a conversational thing, and so, and people liked it, and then I started incorporating other things in that. So it's been great exploring things, looking at people, trying to see what they do, but placing them in different worlds, that's always a non-trivial thing to do, because if you're trying to do science fiction especially, I normally try to stay away from general typical lifelike situations that we have, but try to bring in some kind of futuristic thing, some kind of speculative thing, so you always have to extrapolate a little bit.
So what are your favorite kind of themes? Like, I'm a big fan of immortality, time, and playing around with that.
So one of my interesting theme that keeps on recurring is, again, trying to explain some ancient mythological thing through science.
Oh, cool.
Also try to bring it up and show how it can have a different reason than what people think of it theologically. So not necessarily slapping a non-existing answer on that. Or I love aliens, but aliens not in the typical way they are shown, because given the size of the universe, there have to be other races.
Yeah.
But given the distances, it's also very difficult for us to necessarily be able to communicate. We don't know whether we'll ever be discovered or whether we will be discovering anyone else. So start a story where things seem to have an alien theme, but then it perhaps turns out that there is a more logical explanation to that coming up from the Earth itself.
So I think not quite aliens.
Not quite alien.
Cool. Well, let me check what time it is. Great. Okay, I guess we'll change topics and talk a little bit about how people, amateur astronomers and everything, play into the picture of astronomy. What I found interesting is you told me that your data isn't valuable because you share it with everyone, and we're looking for answers, but it's not like you could sell off your data that you're collecting. We're sharing that with other countries. So talk a little bit about data and a little bit about how citizens can participate?
Right, so the specific term that is used jokingly with astronomy data is that astronomy data are worthless. What that means is that so data scientists typically have to pay money to get into medical data or financial data, whereas with astronomy data there are so many data sets out there that you can just go to websites and download the data. So it's only in that sense it is worthless, but people love the data. And so we often set up some data challenges. And so we want citizen scientists, but also computer scientists to get involved. We want them to start participating in our projects. And one of the projects that Sloan Digital Sky Survey had started was Galaxy Zoo, where they wanted people to help classify them between spiral galaxies and elliptical galaxies. So they were showing images of these kinds of galaxies, and people could log in. They got a tutorial, and then they would go and click. And so there are very interesting stories related to that. And one story that I remember is from a Dutch school teacher. Her name was Hanny, and she found a blue area near a galaxy, which was not really part of the galaxy, but you're looking at these images, beautiful images, and then she said, "What is this?" She called it a thing or thingy, and the word for thingy in Dutch is voorwerp, so that became famous as Hanny's voorwerp because it was a new kind of object astronomers didn't know about. It's very likely an ionizing echo from the galaxy nearby. And so many such objects were found later on because people went after that and looked at. So these kinds of interesting discoveries can happen when we are looking at very large data sets, and that's the power of big data set. That's why we want to involve a large number of people to look at the data sets.
So what are people better at doing and what are machines better at doing?
Okay. So one of the first machine learning, not necessarily the first one, but something that was fairly popular some time back was a neural network, a simple neural network.
Yeah.
And it was based on how our neural network was supposed to be working. It was not exactly the right model, but that was the basis. And so what we often say is that when we do classification by looking at things, we're using our neural networks, versus when machines are doing that, using the neural networks there. And it's a very good combination that one needs to use because we don't fully understand our consciousness, how exactly we can make some decisions. But based on how the large number of neurons we have, they connect to another set of neurons and how the electric current flows in them, what decisions are made. So that is the modeling that computer scientists are trying to do in these things. So the deep learning that I mentioned earlier, that's the model that's being recreated here. So it's always a good idea to use the combination of both, but then deep learning is where a large number of patterns are being found automatically. What happens when that happens is that it is a big black box and we lose some kind of interpretability in that. So for that, going back to humans or coming back with some visualization is the important thing, looking at that.
So yeah, computers are better at bulk analyzing the data, but you'll lose the nuances. It might not catch something.
Or you may not be able to see exactly how it's doing something or understand that.
Okay. So is there a concern that we'll start relying too much on the computer analysis of it and lose...
Hopefully not at the level of scientists, but at individual level people are already doing that not too many people can multiply in their head, for instance. So they pull out a calculator and try to do that. In that sense, we're already doing that.
Yeah, we're aided in every sense by technology.
Right. And it's fine to rely on technology, of course.
Yeah. So over the years, what are just something that stands out, a discovery, gravitational waves, I'm sure has played a part for you with LIGO, but so you've been in astronomy for 20 years or so. What's some major discovery that we've found or something exciting that you were there for?
Well, yeah. So these large-scale surveys, sky surveys, have been finding lots and lots of things. So some of the things that we found were gravitational lenses. So what happens in a gravitational lens is that there is a body of mass in between a distant source and between you, and then we can see the light bending around that object and it comes towards you. So because light travels in a straight line, though it bends like this and comes to you, what we see or feel is that it's coming from those directions. So instead of a single object, you can see multiple images. So we were able to find some images of those kinds. And then there have been large number of mappings. So one of the surveys that I worked on, the Catalina Sky Survey, it has found thousands of asteroids, and some of them were predicted to hit the Earth before they hit the Earth. So we were able to find some, and then people could do so NASA talks about sending astronauts to asteroids and getting material from there, but this was the best mission that we could do of recovering things, because if you predict something is going to hit the Earth and where it is, then you can go to that point on Earth and recover that asteroid, right? So in Sudan there were some such pieces that were picked up.
Oh, that's awesome. Yeah, and was this part of the thing where you were named, an asteroid named after you, or this was different?
No, so it was because of my it was because of my work on this survey that an asteroid was named after me. So there is an asteroid that is called Mahabal. It is a main belt asteroid that's in all the asteroids together.
Yeah.
And so the asteroid name is an interesting thing. Unless an asteroid has completed a couple of orbits, those don't get named. Because what if you name an asteroid after someone and then it comes and hits the Earth? Then who's responsible?
Oh, we can blame that person. Yeah, speaking of, I read today that an asteroid came very close to the Earth just within the last week or so, passed between the Moon and the Earth. So, but asteroids come close to being the Earth all the time. Right.
Smaller ones.
Smaller
not,
ones.
Not
This was
big
a
ones.
large one. So what are we kind of doing to watch for asteroids?
So these surveys that are essentially doing that. So there is one of the main aims of many of these surveys is to be able to catalog all the asteroids that we know down to 150 or 100 meters. Because then we can be sure of keeping a track on their orbit, and if one comes too close, because what happens is that planets like Jupiter often can nudge some of these asteroids, and they can change their orbits, and then it can come towards the Earth, say. And so there are many things that could be done in principle if an asteroid we detect could be coming towards us to try to move it away, so long as we know about it well enough in advance, and so long as the space program is operational.
Do we have an Armageddon type plan where we shoot someone onto it and blow it up from the core?
Unfortunately not yet.
No. So how do we stop an asteroid if it's coming?
Well,
Put the stop sign and
Yeah.
one could think of something like putting something to make it rotate in a different way,
Okay.
and then one could think of blasting it off.
Yeah.
Or there is a simple theory: if it's far enough away, then one could say paint one side of it with one color so that its reflectivity can change and its rotation can change and it can
Oh,
go
that's
away.
interesting.
But again, you'll have to spray a lot of paint there and so that
It'd
it
be hard to
sticks
get
and
all
so.
of that.
that's a
paint
lot
there
of
in
spray
time.
paint.
Yeah.
Yes,
Who would think that you could spray paint an asteroid though to stop it from colliding there?
these are what are Gedank and Berish, right? Thought experiments.
Yeah, yeah.
So
It's
then,
cool.
then engineers can think of how that can be made practical, how that can be
Right.
turned into reality. So.
Yeah, that's awesome.
Could that really happen? Could they actually literally spray paint the side of an asteroid that could destroy the Earth and get it to rotate in a different direction by doing
Yeah,
that?
right. And so for
Or would they
instance,
have to point the asteroid in a different...
no. So what will happen is that the asteroid is rotating as it is, and if you were to paint one side white and the other side black, so that the reflectivity is completely different between the two sides, there's a differential heating that happens, and as that happens, that could change things enough. Again,
that's been
it
proven?
depends on the size of the asteroid, the distance of it, how fast it is rotating, what fraction of it is facing the sun at a given time, and things like that.
Oh man, that takes all fun out of it. Get out of it.
That's pretty cool though. Well, I guess we'll open it up to some questions. Anyone have questions for Ashish? Matthew?
Well, I understand that it would be really neat to observe a nova or a supernova shortly after it goes boom. Is Betelgeuse regarded as a possible candidate?
It is, yeah. And Yeah, but we don't know when, right? Yeah. So, I hope not in my lifetime.
Why?
Well,
Close.
it'll be
I
really,
got
really,
you.
really, really energetic.
Eli.
Yeah, my first question, when you started talking about blazars and galaxies and whatnot, what is the technical spectral visible light color of the Milky Way?
A visible light color of Milky Way. The Milky Way is like any other galaxy, right? It's a spiral galaxy, so you can see all the stars in the Milky Way galaxy of different kinds. So the optical signature you can see, so from 3000 to 10,000 angstrom, all kinds of things. So there will be.
Is there like a general hue to it though? Like,
So there are red stars and there are blue stars, if that is what you are. So there are some young stars in
some
our.
are Democrats. Right?
Yes. So it's a good mixture of all kinds of stars that we see.
Bill?
That affects when one side of an asteroid is brighter than the other, right? And do you recall reading about it? What's it called, the Yarkovsky effect or something like that?
Sorry, I missed the first part of your sentence.
That effect, where one part of an asteroid is bright and the other part is.
No, I'm not sure.
Tsiolkovsky? Perhaps Tsiolkovsky after the.
No. Yarkovsky or something like that. Sorry.
Any other
I
questions?
have a quick question.
Yeah.
Kind of rather silly. Are there any asteroids affecting the Earth at this time?
How many asteroids?
Any asteroids that are headed toward Earth at this time?
Oh, there are no specific ones that are headed towards Earth as such. There are some 2 or 3 that we know of that we think could come in 20-30 years, but again, they're not necessarily going to impact the Earth, but those are the ones that are being watched more intently. Because typical asteroid orbit is only 3 to 4 years, right? The standard ones they go around.
What's the odds of somebody actually finding an asteroid? I mean, I don't really pay attention a lot to this, but you watch enough Armageddon movies and you start to question them. And I'm a huge Armageddon fan, by the way. And I know it's not reality, it's fantasy. But I'm just curious if an asteroid were of that size to ever even approach the Earth, what would really happen?
We'll know enough in advance if it is a big asteroid, right? And if it is too close to us when we discover it, there may not be too much that we could do.
How far away do you think you could discover a large asteroid?
So by definition, the asteroids are not too far off, right? But if we
Yeah.
discover it the moment it veers off its main orbit, then
okay.
that gives us long enough time.
Yeah.
Right?
Okay, fair
Well,
enough.
after all, the asteroid, which basically killed off the dinosaurs, was not all that large.
Right.
I mean, yes, when the first part of it hit the Earth, still the back part of it was still in space, but compared to other asteroids, it was not quite a pebble, but it wasn't huge.
Right. And
Eli, and then Gavin.
yeah, what I wanted to say, I watched an entire documentary on how to prevent an asteroid impact that could be serious, like, if something's 5 or even 3 kilometers or more in diameter. And a lot of the theories seemed outrageous, but the one I think towards the end was the most likely. If you use like an Apollo rocket that can reach the moon in 4 days, and you essentially fortify something like that, you can send a nuclear warhead into space, and even if it only hits the asteroid when it's about a month from impact, if it hits like a side of it, it will knock it off its course, and it will miss the Earth.
sure, yeah.
Something like that seems no problem.
Okay. Gavin.
You mentioned that you had published some of your science fiction stories in India. Can you tell us a little bit about the science fiction?
Scene in general.
Yeah. That's a great question.
So actually, it's not a very good scene in general. And so in Marathi, my mother tongue, there are a couple of annual magazines that publish science fiction only stories, but they also tend to be more science fantasy, so not so much hard science fiction. And similarly, there are 3 or 4 other vernacular local languages where there are a couple of magazines each. But many times these stories tend to be, I won't call them naive, but rather of a similar nature, not too many different ideas that are being tried in that, and they many times are tied to the society. So there is a very strong story and society base rather than being more speculative, futuristic. In English, again, there are a couple of magazines and newspapers sometimes publish them, but it's something similar, and that's partly because there is so much that is being produced all along that it's not easy to pick good stories and bring them up and make them popular. Only in the last few years it has looked up a little bit, but in general I won't say that the scene is great. So I personally belong to an online group. Most of them are in Maharashtra, the state I come from, where Marathi is spoken, and we make a challenge for ourselves for every month. So we take some loose topic on which each of us tries to write a story and give each other feedback, and then these stories are sent to publication. So because of this group now, there have been 2 or 3 anthologies that have been published recently, and we are making an effort to go out to editors and educate them about science fiction. So we call them sometimes to our meetings, and they are forming up slowly and saying that we could have this as a good thing. And they of course want that to be a capitalistic thing, because if they put in money, they want their money back at least. So which is a fair thing to do. And so the sellability is what's the main thing.
Is there a lot of English science fiction translated and published in India?
There is. I would say it would be roughly the same amount as local things that are published. But many of the English translations tend to be not so much proper science fiction, but more the thriller kind of science fiction, which is in between.
Oh, one more question.
I have a question. Is any of your stuff available on Amazon?
Sorry?
Any of your stuff available on Amazon?
Amazon, no. So what I want to do is that maybe after another half a dozen stories, put together that into a book. The other thing that I'm going to be doing is start translating my own stories into English and then put them together.
Yeah, we'd be interested in reading them if we could. So let us
That's
know
where
when
I
that
was
happens.
going. Thank you. I'm reading my mind.
Yeah. All right. Well, that's all the time we have. So thank you, Ashish. This was
Thank
great.
you.